Okay, let's dive into this explainer and learn how to decode the secret language of chemistry. Have you ever looked at the back of a product label and felt like you were literally reading an ancient, indecipherable text? Well, you're not alone. But here's the thing. Chemical nomenclature is actually a highly logical system. It's got a specific set of grammatical rules. Once you learn the affixes, the prefixes and suffixes, you can translate almost any chemical name right into its exact formula. Think of it less like memorizing a giant dictionary and way more like learning the rules of a secret code. So here's our Codebreakers roadmap for today. We'll start with the language of compounds, then move into ionic compounds in the stock system. After that, we've got molecular compounds and prefixes, cracking binary acids, the oxy-acid conversion rules, and finally, naming hydrated compounds.
All right, part one, the language of compounds.
You see, historically, chemists just named things based on how they looked, tasted, or even where they came from. But if we just use common names, then we get completely confused across different regions and languages. The ambiguity of a common name like washing soda brilliantly illustrates this. Like, what even is that? It tells us absolutely nothing about its chemical makeup. Now compare that to its precise, rule-based IUPAC name, sodium carbonate decahydrate. Boom. That systematic name tells a trained chemist exactly what atoms are present and in what exact ratios. But before we get into the really complex stuff, let's establish our baseline. If a substance contains only two different elements, then it's known as a binary compound. This is literally the simplest place to start our translation. Whether it's a metal reacting with a nonmetal or two nonmetals just bonding together, binary compounds form the absolute root of our naming logic. Moving right along to Section 2, ionic compounds and the stock system. So for a standard ionic compound, the rule is pretty simple. Name the metal, then name the nonmetal, but change its ending to the suffix "ide." For example, sodium and chloramine become sodium chloride. Simple enough, right? But if the metal is a transition metal, those elements sitting right in the middle of the periodic table, then it often has a variable charge. And if it has a variable charge, then its specific positive charge must be indicated with Roman numerals in parentheses. We call this the stock system, and you figure out that charge by looking at the balanced negative charge of the anion it's attached to. And this brilliantly illustrates why those numerals are absolutely crucial. Let's take iron. Iron is a transition metal that can have a +2 or a +3 charge. If we just simply say iron chloride, then we literally wouldn't know if we're dealing with iron 2 with a +2 charge or iron 3 with a +3 charge. These are completely different compounds with totally different properties. So throwing that Roman numeral in there unambiguously solves the problem. Okay, Section 3, molecular compounds and prefixes. Now, because covalent bonding allows for a ton of variation, the names must explicitly tell us how many atoms of each element are actually in the molecule. So the crucial point here is this. If you are dealing with binary molecular compounds, then you use exact Greek prefixes to specify the number of atoms. It's mono for 1, di for 2, tri for 3, tetra for 4, all the way up to deca for 10. So if you have a compound with 1 nitrogen and 3 fluorines, it's nitrogen trifluoride. But watch out, because there's a huge grammatical exception in this system. If there is only one atom of the very first element in the formula, then you always omit the mono prefix. And honestly, you've probably used this rule without even realizing it. Think about CO2. We call it carbon dioxide, right? Not monocarbon dioxide. However, for the second element, the mono definitely stays, which is exactly why CO is carbon monoxide. All right, on to Section 4, cracking binary acids. Here is your incredibly logical if-then rule for this one. If your anion ends in the suffix "ide," like chloride or sulfide, then you apply a very specific formula. First, you change the word hydrogen to the prefix hydro. Second, you modify the non-metal ending from "ide" to the suffix "ic." And finally, you just add the word acid at the end. So hydrogen chloride gas dissolved in water, that becomes hydrochloric acid. Hydrogen sulfide, that becomes hydrosulfuric acid. It's a highly predictable step-by-step pattern. Next up, Section 5, the oxy-acid conversion rules. Now, this is where it gets really interesting. We completely drop the word hydrogen here. If your polyatomic anion ends in 8, like the chlorate ion, then it becomes an IC acid, so chloric acid. But if you remove one oxygen atom, the anion ends in ite, like chlorite.
And if the anion ends in "ite," then it becomes an "us" acid, chlorous acid. So just remember, "ate" goes to "ite," and "ite" goes to "us." Easy, right?
But wait, there's more. Some elements, especially halogens like chlorine, form a whole series of oxyanions. If we have even more or fewer oxygen atoms than our standard ate and ite forms, then we bring in two specific prefixes. If we have one more oxygen than the ate form, then we add the prefix per, giving us terms like perchloric acid. Conversely, if we have one less oxygen than the ite form, then we add the prefix hypo, which literally means under. That gives us hypochlorous acid. So per means more and hypo means less. Okay, so we've covered ionic compounds, molecular prefixes, and the kind of complex rules of acids. But before we wrap up this Codebreakers guide, I have to ask one final, really cool question. What happens if an ionic compound traps intact water molecules directly inside its solid crystalline structure? Which brings us perfectly to our final section, naming hydrated compounds. If a compound has water molecules attached as integral components of its crystals, then we simply recycle our Greek prefixes from our molecular compounds lesson earlier and attach them to the word hydrate. Remember our washing soda example from the very beginning? Its real name is sodium carbonate decahydrate. Deca means 10, so there are 10 water molecules associated with every single unit of sodium carbonate. Another classic example is copper 2 sulfate pentahydrate. The penta tells us there are exactly 5 water molecules trapped right inside that beautiful blue crystal. And just like that, you've unlocked the whole system. You now know that "ide" denotes a simple binary anion, that Roman numerals indicate variable metal charges, and that Greek prefixes tell us exactly how many atoms or water molecules are hanging around. You know that ate ions make ic acids, and ite ions make us acids, perfectly flanked by per and hypo for maximum precision. So, armed with the prefixes and suffixes of this chemical Rosetta Stone, the very next time you look at a wildly complex ingredient label on your food or household cleaners, what secret chemical language will you decode first?